Hey everyone, and welcome to this explainer on Chapter 11 of Clean Code. Today, we're taking those macro-level software architecture concepts and turning them into actionable blueprints for your daily development. Basically, we're going to take the principles you already use to clean up your functions and classes and elevate them to the absolute highest level of abstraction, the system itself. Now, to really wrap our heads around managing the sheer, immense complexity of modern software systems, we gotta ask ourselves a question. How do humans successfully build and manage sprawling physical cities? I mean, think about it for a second. There is no single person managing every tiny detail of a metropolis. Cities work seamlessly because they've evolved appropriate levels of abstraction and modularity. The person managing the water supply doesn't need to understand the big picture of the traffic light programming, which honestly is probably for the best. Our software systems should strive for that exact same structure, where individuals and components can work effectively without needing to comprehend the entire overwhelming whole. Okay, let's take a quick look at our blueprint for today. We're going to cover 1. Building a software city, 2. Construction versus use, 3. Scaling cross-cutting concerns, and 4. Test driving your architecture. All right, let's jump right into Section 1, Building a Software City. Writing clean lines of code absolutely helps at the lower levels, like picking good variable names or writing short, punchy functions. But here's the thing. We need to apply that exact same discipline to stay clean at the highest levels of system abstraction. Unfortunately, a lot of software teams just fail to organize their systems with the kind of strict separation of concerns that city planners use every day. And what happens? We end up tangling all these different responsibilities together, which makes the whole system incredibly fragile as it grows. It's like building a skyscraper on a foundation of toothpicks. Moving right along to Section 2, Construction versus Use. Picture a massive new hotel being built. During construction, what do you see? Bare concrete, towering cranes, people in hard hats. It's messy, right? But flash forward a year, the building is wrapped in clean glass windows, and the people inside are guests, not construction workers. Well, our software system should work the exact same way. The startup process, where we actually construct application objects and wire dependencies together, needs to be completely segregated from the normal runtime logic that takes over once the building is, well, finished. If we mix construction logic, like lazy initialization, right into our runtime processing, we completely break modularity and end up scattering global setup strategies all over the place. So how do we actually pull off this separation? Well, one super simple way is to just move all aspects of construction over to the main module. If you follow the flow of control, all the dependency arrows point away from the main builder and toward the application. This is absolutely crucial because it guarantees the application itself has zero knowledge of that messy construction process we just talked about. It simply expects that all its objects have been perfectly built, wired together, and are ready to go. But wait, what if the application actually needs control over exactly when an object gets created? Say you have an order processing system that needs to create line items on the fly. In that case, we can use an abstract factory pattern. The application code triggers the creation, sure, but the nitty-gritty details of how that creation happens are still kept safely over on the main side of the line. Your application stays entirely decoupled from those messy construction details. Now, an incredibly powerful mechanism for separating construction from use is dependency injection, or DI. Essentially, this is the application of inversion of control to dependency management. So rather than an object actively instantiating its own dependencies, which, by the way, totally violates the single responsibility principle, it acts as a completely passive object. It basically throws its hands up and surrenders the responsibility of creating its dependencies to an authoritative mechanism, like a dedicated container. The real takeaway here is that a DI container totally takes over the instantiation process. True dependency injection means your class takes absolutely no direct steps to resolve its dependencies. None. It just provides setter methods or constructor arguments. Then, a container, like the Spring Framework in Java, swoops in and dynamically wires up those dependencies on demand. It usually does this using configuration files or annotations, leaving your core objects completely, blissfully ignorant of how the system is actually stitched together under the hood. All right, let's dive into Section 3, Scaling Cross-Cutting Concerns. Building a physical city requires these massive upfront blueprints because, let's face it, you can't exactly pick up and move a paved highway once the concrete dries. But software systems, they're totally unique. they're ephemeral. As Robert C. Martin points out, their architectures can grow incrementally from simple to complex, but there's a catch. This only works if we maintain proper boundaries between different functional areas. If we fail to separate those concerns, our software just morphs into an unscalable, tangled mess.
And as we scale up our software city, we inevitably run into what we call cross-cutting concerns. These are system-wide behaviors. Think logging, database persistence, or security. The big issue here is that these concerns threaten to scatter identical boilerplate code across all of our beautifully isolated domain objects. Like, say you want to save an object to a database. Suddenly, your pure business logic is completely infested with database connection commands. Not great, right?
To fix this, we bring in aspect-oriented programming, or AOP. AOP is basically a technique that restores modularity for these cross-cutting concerns. It lets you declare aspects that specify exactly how the system's behavior should be modified, and then it delegates those heavy infrastructure tasks to a framework. And the real magic of AOP? These modifications are applied completely non-invasively, so your core business logic stays as pure, decoupled, plain old Java objects, or POJs, totally untouched by the messy realities of databases or security protocols. It helps to think of this AOP framework kind of like a Russian nesting doll of decorators. Imagine your pure domain object, let's say it's a bank, sitting right there at the very center. It is invisibly wrapped by a data access object decorator, which might then be wrapped by a transaction decorator, all handled seamlessly by the framework. The client application? It thinks it's just talking directly to the bank object, but in reality, the framework is invisibly managing the database connections and transaction states on the outside. And the bank object itself? It knows absolutely nothing about it. And that brings us to our final part, Section 4, test driving your architecture. So if you successfully decouple your domain logic from your architecture using those POJOs and aspects we just talked about, you completely eliminate the need for a massive big design upfront. In fact, big design upfront is actually kind of harmful because it makes you psychologically resistant to changing course later on when you learn new things. Instead, you can start with a naively simple architecture, deliver working user stories incredibly fast, and then just add robust infrastructure like caching or load balancing only when your scale actually demands it. Having this kind of agility allows us to postpone major architectural decisions until the absolute last possible moment. Now, I know what you might be thinking. That sounds lazy. But actually, scratch that. It's highly strategic. A premature decision is essentially made with suboptimal knowledge. By holding off until the last minute, you make sure your choices are informed, agile, and just in time based on the most recent and accurate feedback from your actual project. It lets the system evolve naturally and gracefully. Because of all this, the architecture itself can literally be test-driven and evolved, exactly like your lower-level code. So what does the optimal system architecture actually look like? Well, it consists of modularized domains of concern, it's built with plain independent objects, and it's integrated using minimally invasive aspect tools. When you build your system this way, the architecture simply gets out of the way. It lets your team focus all their creative energy on what really matters, delivering actual, tangible value to the user. To wrap up our explainer today, whether you are designing massive, sprawling systems or just individual modules, never forget to use the simplest thing that can possibly work. Unnecessary complexity is literally the enemy of clean code. Which leaves us with one final provocative question for you to take back to your own codebase. What needlessly tangled structure can you begin untangling today? Thanks so much for joining me on this deep dive, and happy coding.